We will now start the discussion of haloalkanes. Now, before starting the discussion, we should know two simple things. The first thing is valency of carbon is 4. That's an important point, even though it is simple. Now, the second thing to remember is that when a single bond is broken, two valencies are created on the atoms forming the bond. So a single bond AB, when broken, we get atom A with a valency and atom B with a valency. Now atom A with valency and atom B with valency can unite to form an AB bond, which is the reverse of the first process. Now valency is like our hands. You give your hand for shaking with another person's hands. So when two hands combine, a relationship arises between two persons. Similarly, when two valencies, free valencies combine, a relationship, that is bond, arises between two atoms. So these two are the main points to remember. That is, valency of carbon is 4, and when a bond is broken between two atoms, free valencies are created over the atoms, and when two atoms with their free valencies combine, a bond is formed. So these two simple principles are to be followed in organic chemistry. Now coming to preparation of haloalkanes, starting from alcohol. Now the first important reaction is the reaction between alcohol and HCl. HCl can be in the gaseous state or as a concentrated solution of hydrochloric acid, and a catalyst is used, that is zinc chloride. And then the valency created by breakage of ROH bond. So when RO bond is broken, a valency is created over R and a valency is created over OH, that is oxygen atom. And when HCl bond is broken, a valency is created over hydrogen and a valency is created over chlorine. Now the valency created over hydrogen combines with the valency created over OH, producing HOH or H2O. Now the valency created over R combines with the valency created over Cl, forming RCl. And zinc chloride, preferably anhydrous zinc chloride, is a catalyst. Now zinc atom has the configuration 3d10 4s2. And in zinc chloride, the ion Zn2 positive is present. And for Zn2 positive, the configuration is 3d10. The 2 electrons in the s orbital are removed to get zinc ion. So there are vacant s and p orbitals. Now into these vacant orbitals, that is 4s orbital, an electron pair of oxygen may be received, so that we get OZN bond. Since a pair of electrons are donated, one electron goes to the zinc atom, forming a negative charge on zinc and a positive charge on oxygen. Now there are two cases to be considered. If R is a primary alkyl group, for example say methyl group, then it is unable to form a carbocation. So an SN2 reaction results. Now here the HCl molecule ionizes into H positive and Cl negative. Now Cl negative attacks R from the back side. So this as a whole forms the leaving group. So we get CLR or RCl and OH is ZnCl2 negative. So once again, lone pair of oxygen is given to zinc. Now oxygen carries positive charge and Zn carries negative charge. HCl ionizes H positive and Cl negative. Then if R is a primary alkyl group, that is, say for example, methyl group, then it is unable to form a carbocation. So SN2 reaction occurs. Cl minus attack from the back side of the leaving group, and we get ClR, and simultaneous shift of this pair of electron over a positive oxygen means this pair of electron is taken up by oxygen. Then since oxygen gets the share of this R group, the positive charge over oxygen is neutralized. So we get OH Zn Cl2 with negative charge. Then when H positive is removed from Cl negative is removed from HCl, we get an H positive remaining. So when HCl ionizes, we get H positive and Cl negative, and the Cl negative is removed for this reaction. So we get H positive as a free ion. This H positive attacks the lone pair of oxygen in OH, Z and Cl2 negative. Now you may suspect why H positive does not attack this negative charge, that is zinc atom with negative charge. Now the reason is that zinc provides a very large 4s orbital with a very low electron density, and H positive is a very small ion with a vacant orbital, of course, and the vacant orbital is very small in size. So the overlap between a large 4s orbital with low electron density and a very small orbital of hydrogen positive will be less effective, and the overlapped region will not have sufficient electron density to make the bond a strong bond. So a large orbital overlapping with a small orbital, a large orbital of low electron density overlapping with a small orbital, the bonding is not effective. So H positive prefers oxygen atom, and we get H connected to oxygen, then the positive charge is transferred to oxygen, then this bond will be shifting over oxygen, in the sense this electron pair will be taken up by this oxygen entirely, so that oxygen gains the share of zinc also. So this positive charge is neutralized, and when oxygen gains the electron share of zinc, its negative charge is getting neutralized, and we get ZnCl2 and H2O. So ZnCl2 is a catalyst. Now even if H positive attacks Zn, then we get such a species which will easily remove water by shifting of H, the ZnH bond in this direction, and OH as OH negative, and this H positive and OH negative will combine to form water, HOH and ZnCl2. So the entire thing, starting from ROH and ZnCl2, these steps represent what is called the mechanism of the reaction. And a reader, a viewer of this video is not expected to study this mechanism, but you understand such mechanisms are there. Just only go through this mechanism and then you neglect it, and you rely upon the symbol equation shown by this step. But if you are challenging, you should study this mechanism also, because in the syllabus you are expected to study some mechanisms, and if you are familiar with the such simple mechanisms, then you will be able to study those mechanisms. Not only that, you will be able to study more reactions. Now, by studying this mechanism, we will remember that zinc chloride is a catalyst in the reaction. Now, coming to a second method, that is the reaction between PCl5 and ROH. Now, before that, about the first reaction, that is the reaction between ROH and HCl in presence of ZnCl2. If R is a tertiary alkyl group or the alcohol is a tertiary alcohol, then there is no need of zinc chloride. Even in the absence of zinc chloride, the reaction may proceed. In that case, ROH first reacts with H positive to produce ROH2 positive. Now, this OH2 positive is a good leaving group, and that will take up the electron pair producing R positive. So, even in the absence of zinc chloride, reaction with a tertiary alcohol can proceed. Now, there it is an SN1 process, and I told you earlier that SN1 transition state is having a lower energy than SN2 transition state. So, lower the energy of the transition state, lower the energy of activation, and higher is the rate of the reaction. So, a tertiary alcohol gives an immediate reaction, a speedy reaction with HCl, even in the presence or absence of zinc chloride. Usually anhydrous zinc chloride is preferred for this reaction. Now, when concentrated HCl is used, it contains slight amount of water. So, when an alkyl halide is formed in a medium containing water, since alkyl halide is insoluble in water, initially we get a milky appearance or called opalescence. Now, if a tertiary alcohol is the starting material with the zinc chloride, anhydrous and HCl, we get an immediate opalescence showing an immediate reaction by SN1 mechanism. If it is a secondary alcohol, then we get the opalescence only after a few minutes, 5 minutes later we get the opalescence on shaking the mixture. So, it is a little slow because a secondary carbocation is less stable than a tertiary carbocation. Now, with a primary alcohol and anhydrous zinc chloride and HCl, you have to heat the mixture to get an opalescence. So, this can be used as a test for the three types of alcohols, that is primary, secondary and tertiary. Tertiary gives an immediate opalescence indicating the formation of RCl. Secondary gives an opalescence only for shaking after 5 minutes, and a primary gives the opalescence only on heating, because a primary undergoes SN2 reaction which need energy in the form of heat to reach the transition state. Because of its high energy of activation, you have to heat the mixture, supply energy to reach the transition state, and so on. Now, then the second reaction, that is alcohol reacting with PCl5. Now, the reaction leads to the formation of RCl. So, 1 chlorine from PCl5 is reacted with R to produce RCl. So, OH is getting removed from ROH and Cl is getting connected. Cl is supplied by PCl5. Now, 1H and another Cl combined to form HCl. So, 2 Cl are removed from PCl5. Then The oxygen atom remaining will combine with phosphorus and 3Cl, giving POCl3, and that molecule is called phosphoryl chloride. PHOS PHORYL, phosphoryl chloride. Now let us see how the reaction happens. Again, I told you these mechanisms, one thing need not be correct, because most of the mechanisms are fabricated by myself, and so they are not absolutely correct, and I suggest you should not study these mechanisms, but go through these mechanisms and understand what happens. Then we can remember how the products are formed. Now, first of all, the lone pair of oxygen of alcohol is given to phosphorus. Then the valency of phosphorus increases from 5 to 6, and phosphorus gains a negative charge, so there is later crowding of groups around phosphorus. So to avoid the negative charge of phosphorus and the crowding, because this group as a whole gets united to phosphorus, one chlorine is removed as Cl negative. So we get Ro positive with H connected to phosphorus, and 4 Cl groups plus Cl negative. Now this species will be attacked by chloride ion if R is a primary alkyl group, for example methyl group. Then chloride goes behind methyl group, and then this negative charge is given towards R, so that a pair of electron of chlorine, of course, a pair of electron of chlorine will be donated towards R, and that is shown by an arrow starting from the negative charge in a position in between chlorine and R, indicating that a bond is formed between Cl and R using a lone pair of chlorine. Now simultaneously, to maintain the valency of carbon, this bond will be shifting in between O and P. Now this can shift towards oxygen atom, neutralizing the charge. That is one possibility. And another possibility is that this bond will be directly shifting in between O and P, means you think mechanically, that is, this bond rotates to 180 degree to the position between oxygen and phosphorus, making it a double bond, and to maintain the valency of phosphorus, this chlorine is removed as Cl negative. Now always phosphorus will be having a tendency to take up electrons, because its oxidation state is +5 in this case, so that we get ClR, then OH positive double bond P Cl3 plus Cl negative. Now this OH bond will be polarizing towards O positive. That means this pair of electron will be entirely taken up by oxygen atom, and during that process the electron of hydrogen is given to oxygen, and this extra electron neutralizes the positive charge. So we get POCl3 and H plus Cl negative, H positive plus Cl negative, giving HCl. So that is the mechanism of the reaction. Again, I am emphasizing the fact that you go through this mechanism. You need not study this mechanism, but if you are compelling, then you study it. And again, I said some of these mechanisms are fabricated by myself, so they need not be correct. But to understand the reaction, you must go through these mechanisms. Now, if R is a tertiary or secondary alkyl group, then SN1 reaction occurs. That means RO bond shifting over this positive charge, or it may shift in between O and P. Then if RO bond is shifting over positive charge, means if the bond pair is taken up entirely by oxygen, then the share of carbon, that is R, is taken up by oxygen, and then an extra electron is gained by oxygen, so that the positive charge neutralizes, we get neutral oxygen atom, hydrogen. Then the OH bond will be shifting in this direction, giving a double bond between P and O, and here H positive is released, a Cl and Cl negative is removed from this part, and that is a slow process. That is not a slow process, but this one is a slow process, and this process is a fast one. So the slow here means this step as a whole is slow, but this reaction is not slow, it is fast. So you shouldn't confuse this change with this reaction. Here POCl3 and HCl are formed by a fast reaction, but this step is a slow step, that is formation of R positive and OH PCl3Cl. That is a fast, slow reaction, but this reaction is a fast reaction. And then the second step, that is R positive plus Cl negative in RCl, that is a fast reaction, because SN1 reaction involves two steps. This is step 1, which is slow, the rate determining step, that is formation of carbocation, and then carbocation combining with nucleophile, that's a fast step. So once again, the lone pair of oxygen is given to phosphorus simultaneously to maintain the valency and to nullify the negative charge. Cl is getting removed as Cl negative, we get a positive charge over oxygen, then Cl negative, and if R is a primary alkyl group, example methyl, this R is a methyl group, then it cannot give a stable carbocation, so Cl negative attacks from the back side. Then here two things may happen, this pair of electrons taken up by oxygen nullifying its positive charge, or this pair of electron is moving directly to the position in between oxygen and phosphorus, that is, you think mechanically the bond is rotating 180 degree, so that it comes in between phosphorus and oxygen. Then we get this species CLR plus O positive H double bond P Cl3. Then this OH bond will be shifting over oxygen, in the sense this pair of electron is completely taken up by oxygen, so oxygen gets a share of an extra electron of hydrogen, so that its positive charge is getting nullified, neutralized, and then Cl negative. So we get POCl3 and HCl. This compound is called phosphoryl chloride. Then if R is a tertiary or a secondary alkyl group, then SN1 reaction occurs. Here R positive is made free. Now this pair of electron may shift over oxygen, or this may shift in between O and P, then Cl is eliminated like this, so that we get R positive and OH PCl3Cl, which is low. Then this change is a fast one. Then the R positive formed in this low step combining with the Cl negative to get RCl, which is a fast reaction, that is SN1 process. Now reaction with the PCl3 can produce an alkyl halide. Now the equation is 3 molecules of ROH combining with the PCl3 producing 3 RCl and H3PO3, and this acid is phosphorus acid, you know. As usual, the lone pair of oxygen is given to phosphorus, and Cl is removed as Cl negative. Then we get ROH positive, PCl plus Cl negative. Now here the pair of electron will be shifting over oxygen, because the oxidation state of phosphorus here is +3, whereas in PCl5 it is +5, so it is more electron demanding, so that the bond will be shifting towards phosphorus in the previous case of PCl5. Here the bond will be shifting towards oxygen, in the sense this bond pair will be entirely taken up by oxygen. Now if R is a primary alkyl group, example methyl, SN2 reaction occurs, that is the chloride ion freed here will be attacking R from the back side, the alkyl group is attacked from the back side, and this as a whole forms the leaving group. So this pair of electron will be shifting over oxygen, in the sense will be taken up by oxygen, and since the share of R is also taken up by oxygen, it gets an extra electron neutralizing this positive charge. We get ClR, of course the inverted configuration if R is an optically active group. Then OH and PCl2 are formed. Now this Cl again can be removed by reacting with another alcohol molecule. So another alcohol molecule attacking this P, where the lone pair of oxygen atom is given to phosphorus with the simultaneous removal of Cl negative as shown here. Then we are able to get a second molecule of RCl by the same procedure. Then one chlorine is remaining, so that a third molecule of alcohol can react with the product formed. Here the final product formed will be POH OHCl, and the third molecule of ROH can react with this species, producing POH, POH and POH, that is 3 OH groups connected to phosphorus. Now due to the repulsion between this lone pair and bond pairs, this molecule is unstable. Anyway, this molecule is unstable, that is found, and this molecule comes to a stable structure by a simple rearrangement. There the POH bond, there are two POH groups. Now this bond will be shifting in this direction, creating a P double bond O. So P double bond O, OH and OH, and there is H positive formed from this OH group. There is a lone pair. Now this lone pair is given to H positive. We get PH double bond O, OH and OH. This is actually phosphorus acid. So this is phosphorus acid. It's not POH thrice, but H, P double bond O, OH and OH. So this is the structure of phosphorus acid. So this is unstable, rearranges to this one, maybe due to the repulsion between lone pairs and bond pairs. So here there is no lone pair in the final structure of rearrangement. So that is the mechanism of reaction between PCl3 and ROH, 3 ROH molecules, indicating 3 Cl are removed by 3 OH groups, and we get 3 RCl and H3PO3, that is phosphorus acid. Now coming to the reaction between an alcohol and another molecule called thionyl chloride. Thionyl chloride is SOCl2 having a structure S double bond O Cl and Cl. Now we can understand simply the reaction by breaking OH bond. We get H with a valency, then Cl bond is broken, so that we get valency over Cl and HCl is removed. Then the remaining oxygen here combines with SO to produce SO2, that's a gas. A gas is shown by an upward arrow. HCl is another gas, so that's HCl here a gas, SO2 formed by this oxygen and SO group here is another gas. So we get almost a pure product because the other products are escaping from the medium as gaseous products. So that we can get almost pure alkyl halide by reaction of an alcohol with thionyl chloride. Now coming to the mechanism. Again I repeat, you need not study the mechanism but go through the mechanism, try to understand it so that you may remember this equation. Now the lone pair of oxygen atom establishes a bond with the sulfur, and to maintain the valency the pi bond here shifts over oxygen. We get O positive, O negative, then this. Now again the reverse of this process happens here, means the lone pair is now getting converted to a bond pair. Here a bond pair is getting converted to a lone pair and get negative charge. Here a lone pair over oxygen atom is getting converted to a bond pair, that is the reverse of this process. And to maintain the valency, this chlorine is removed as Cl negative. So this chlorine takes up this pair of electrons. So this chlorine is a leaving group here. And we get ROH positive SO S double bond O Cl. So this is a double bond. Then this removes H as H positive by oxygen positive taking up this bonding pair of electron shown by this arrow. And we get ROS double bond O Cl, ROS double bond O bond Cl and H positive. Now this bond will be shifting in this direction and this bond will be shifting in this direction. You think mechanically. So this bond undergoes a rotation through so much angle and comes in between oxygen and sulfur. This bond undergoes a rotation through so much angle so that it comes in between R and Cl. Then we get RCl. Then this bond is broken, this bond comes over here, so this bond comes over here, so we get SO2 sulfur dioxide. Then of course HCl is another product. So this mechanism is called the SNI mechanism, and the I indicates internal mechanism. And if R is ROH is an optically active alcohol with a definite configuration, then that configuration is maintained in the product alkyl halide also. Now let us see a complete mechanism for an asymmetric alcohol forming the condensation product with thionyl chloride. So this particular alcoholic part combining with the thionyl chloride produces this particular compound. Now this bond will be shifting towards the direction between sulfur and oxygen, and this bond will be shifting in between this carbon and this chlorine. So we get a transition state in which this bond is partly broken and this bond is partly formed. This bond is partly broken and this bond is partly formed. So partial bond here, partial bond here, partial bond here, and partial bond here. Then after the formation of transition state, there is complete removal of this partial bond in this direction. There is complete removal of this partial bond in this direction, and we get chlorine here, and the alcoholic part here and the chloride here are having the same configuration. So it is called retention in configuration. Retention in configuration. Now coming to the preparation of alkyl bromides and alkyl iodides. Now alkyl bromides can be prepared by the action of red phosphorus and bromine and alcohol. So alcohol is reacted with red phosphorus and bromine. Red phosphorus and bromine. Now we say PbR3, phosphorus tribromide, is formed in situ. In situ means inside the reaction, mixture. So it is produced at the time of the reaction by PbR3 is produced at the time of the reaction by heating together phosphorus and bromine, red phosphorus and bromine. Now the reaction between 3ROH and PbR3 gives 3RBr and H3PO3. Now PbR3 is available commercially, but it is not used because of its hydrolysis when on keeping. So PbR3 hydrolyzes to H3PO3 and HBr. Similar is the reaction of Pi3 with water. So even with moisture, Pi3 can react to form H3PO3 and 3HI. So we are not using PbR3 and Pi3 for the preparation of corresponding bromides or iodides. So by using red phosphorus and bromine or red phosphorus and iodine, we can prepare the bromides or iodides. Now iodides are also prepared by the reaction between alcohols and potassium or sodium iodide in 95% phosphoric acid. So alcohol is reacted with potassium iodide in 95% H3PO4 phosphoric acid. So the reaction is formation of alkyl iodide and KOH, and KOH is a base and phosphoric acid is an acid. So acid base neutralization reaction is obtained. And good yields of alkyl iodides are obtained by this method, that is action of alcohol on potassium iodide in 95% phosphoric acid gives a good yield of alkyl iodide. We get an appreciable amount of alkyl iodide by this reaction. So much about the preparation from alcohols. Thank you.